Hi, and welcome to Lesson 5. In this lesson, I'm going to be talking about the shortest path algorithms. Shortest path algorithms, as the name says, is to find the shortest path. They are techniques to find the shortest path between nodes in a graph. Why should you learn about shortest path algorithms? Firstly, they're critical for solving problems in network routing, transportation systems, real-time navigation, and social network analysis. There are a number of applications wherein you would want to find what is the shortest path between two given points. Now, this can be in a network, in transportation, in navigation, in maps, or in social media in order to find how near or far 2 points are in social media to understand will the same content be relevant to a particular person who's connected to the other person or not. Let's talk about the first algorithm in order to achieve this. It is Dijkstra's algorithm. In this, you want to find the shortest path from a source vertex to all other vertices in a graph, and the weights of the edges are non-negative. The first step is to initialize the distance of all vertices as infinity, except the source vertex. Mark it as 0. Use a priority queue to select the vertex with the smallest tentative distance. For the selected vertex, update the distances of its neighbors if a shorter path is found, and you repeat this until all vertices are processed. This is like an overview so that you remember how to perform the algorithm. The complexity using an adjacency list with a priority queue is O of v plus e times log v. The limitation is that it cannot handle negative edge weights. There will be a number of cases wherein two parties are inversely correlated and which might be represented as a negative edge weight. We need to have ways in order to handle these scenarios. Now, let's look at a run through of Dijkstra's algorithm. Let's consider a graph like this, wherein we have these nodes given to us, and the edges represent the different parts, the relationships between each of them. So we have A, B, C, D, E, F, G. Let's add weights to it. Let me add another edge. So our goal is going to be to find the shortest path between the given vertices. So we want to find this from this T is our, so this T is our source vertex, and initially the way we want it is Dijkstra's algorithm uses an array with distances to each of the other vertices. So let me parallelly create an array, and the values will keep updating here. So this is like for A, B, C, D, E, F, and G. And this is going to be my distance. So initially D is 0 and every other distance that we don't know is considered to be infinity. Now let me use the next color. Now, setting this to the current vertex, the distance from here to A is 4. So A gets updated to 4. To E is 2. So E gets updated to 2. After this has been updated, so for me from here to reach here is 4, to reach here is 2. Now, in order to reach C, I'll add these values in C. So this is 4 plus 2, 6, or 4 plus 3, 7. So this is shorter. So I'm going to take this route, and to reach C, it is 6 now. So it comes out as 6. And here the shortest path for G is directly from E. So 5 plus 2, 7. So this becomes 7, and to reach G it is 7, and here it is 6. Once I've reached here, now I want to know what is the next vertex that I can visit. So if I have to reach B, 6 plus 2 is 8. So this is 8. Now the only one left is F. If I have to reach F, so 6 plus 5 is 11, 8 plus 2 is 10, and 7 plus 5 is 12. So I choose this and I reach here, 10. So this is 10. So my final distance matrix is 10 and 7. This is the Dijkstra's algorithm. Let's now look at the other algorithm, that is the Bellman-Ford algorithm. In Bellman-Ford algorithm, you find the shortest paths from the source vertex to all other vertices, even with negative edge weights. So this overcomes the drawback of Dijkstra's algorithm of not being able to handle negative weight. Let's see the algorithm steps for Bellman-Ford. Initialize the distances of all vertices as infinity except the source vertex. Mark it as 0. Relax all the edges v minus 1 times. For each edge u to v with weight w, update the distance as the minimum between the distance of v to distance of u plus w. Check for negative weight cycles. If further relaxation is possible, a negative cycle does exist. With Bellman-Ford, the complexity is v times e. The limitation is that it is slower compared to Dijkstra's for graphs without negative weights. So consider a case wherein everything is positive weight. Performance of Dijkstra's is better than Bellman-Ford. So consider a graph that we have of A, B, C, D, and E, and it is connected like this. I'm also considering negative edge just to have all possible scenarios covered. Now, initially, for the edges, I'm going to have, just for simplicity, let's do a couple of things. Let's have a store of this and the distance array. This is the distance array. So if we see B to D is 2, E to D is minus 1, C to E is 1, B to C is 1, A to B is 5. And initially our distance array, we're starting from A, so that is 0. Everything is infinite. Let me choose a different color for the next steps. Now for each of the relaxations, a few of the checks will be performed. If the distance of B plus 2 is less than D or not, if distance to E plus minus 1 is less than distance to D, if distance to C plus 1 is less than distance to E, if distance to B plus 1 is less than distance to C, and distance to A plus 5 is less than distance to B or not. If the conditions holds, the distance will be updated. Now initially, let's go to B. In this case, our conditions are met. The value for B will be updated to 5 in our distance array. After this, in the second relaxation of edges, we see that the distance to B, let's write it here. The distance to B plus 2, that is 5 plus 2 is less than infinity, and distance to D is 7. So I can update this to 7. Also, distance to B plus 1, that is 5 plus 1, 6, is less than infinity, so distance to C is 6. And I can update that value as well. So we now have two more values and our distance array has been updated. Now in the next turn, the distance to C plus 1, okay, I forgot to add the weight. The weight is 1 here. Let me just write it to 1. So distance to C plus 1 is less than infinity. So distance to E is 7 and I'll update that to 7. So my final distance comes out to be 05677. And this way, now if you see, you might think you might want to stop here, but another relaxation of edge can happen because we have a negative edge here. So 7 plus minus 1 becomes 7 minus 1, which is 6, and actually this 6 is less than 7. So the shortest way to reach D is not 7, but is actually 6. So I can update this here. This is the benefit with Bellman-Ford. You are able to handle negative edge. After the fifth relaxation, to detect a negative weight cycle, since there is no shorter distance for any node that is found, the graph does not contain a negative weight cycle. And Bellman-Ford ends here. So our new distance is 0, 5, 6, 6, and 7. This is the Bellman-Ford algorithm. The third algorithm is the Floyd-Warshall algorithm. In this, you compute the shortest paths between all pairs of vertices. The steps are to initialize a matrix called distance, where distance of ij is the weight of the edge from vertex I to j. And in case it is the source of the destination vertex with no edge, then it is considered infinity. For each of the vertex k, update the distances using the formula of minimum between the distance between ij and distance between ik plus distance of kj. Whichever is the minimum, assign that value to distance of ij. Repeat this for all pairs of vertices. This is the Floyd-Warshall algorithm. The complexity is V cube. The advantage is that it has a simple implementation. It handles negative weights, that is, no negative cycles. The limitation is that it is not efficient for sparse graphs and for sparse large graphs. Now, let's look at the working Floyd-Warshall algorithm. Let's consider the graph to be like this. A to B. Let's see here. D, E. These graph examples are some standard examples that I'm taking from Geek for Geeks, just to get a starting point to explain all the concepts that are there. Now consider this is the graph we have. In case of Floyd-Warshall algorithm, we make use of tables. It makes it much easy. So it is also called as the distance matrix. So we will have, so for A, B, C, D, E, so yeah, these are our distances. So initially, we are going to add everything that we know from our edges. So A to A is 0. If you see, first let's fill out, there's no self loops that we see here. So all distances from the vertex to itself is 0. Then if you see A to B, we can reach in 4, and A to D we can reach in 5 unit distance. We can reach B to C in 1 and B to E in 6. We can reach C to A in 2, and we can reach C to D in 3. If you see here, let me write a better 3. Then from D to C we can reach in 1, and D to E we can reach in 2, and E to D we can reach in 4. Everything else is infinity. After this, we treat node A as the intermediate node and calculate the distance for each of the node pair, wherein we use our Floyd-Warshall algorithm formula, which is minimum of distance ij and the distance of I to say A plus distance of A to J. And this in our general sense was written as like V and V. Right now it is like A because we are starting right there. So in that case, let's pick it up. Let's apply the formula. So we get an update here to 1, and everything else remains the same. Now let's consider B as the intermediate node. So we'll see that B to C can be reached in 6 and B to E in 5. Next, let's pick up C. We'll see that this can be achieved in 5. This can be achieved in 6. Also here 2603, and this can be done in 12. If we look at D now, we can reach B in 4, and we can reach A in 3, B in 7, and 1, 0, and 2. And last but not the least, the vertex E. This instead of 6, we can actually reach this now in 5, and we can reach A in 7, and C also. 12 was pretty surprising in the start itself, but we go through the process in order to update the values. This gives us our final values as, let's see, as 0, 4, 5, 5, 7. Did we miss out on 3? On B, let me just calculate here. This is 3. Then 3, 0, 1, 4, 6, 2, 6, 0, 3, 5, 3, 7, 1, 0, 2, 1, 5, 5, 4, 0. So this completes our Floyd-Warshall algorithm. Let's compare the different algorithms. In comparing, let's look at the graph type for Dijkstra's. It is non-negative weights, whereas for Bellman-Ford, negative weights are okay. For Floyd-Warshall, all pairs are acceptable. The complexities are something that we've gone through in each of the individual algorithms as well. And the key use case, if you're working with routing kind of applications and weighted graphs, use Dijkstra's algorithm. If you want to detect negative cycles, use Bellman-Ford. If it is dense graphs with all pairs, use Floyd-Warshall's algorithm. Let's look at a few applications of finding the shortest path. The first is network routing, optimizing data packet routes in computer networks, like OSPF uses Dijkstra in real life. Transportation systems, whether it's GPS or navigation, when you have to find the shortest paths in roadmaps, you again need shortest path algorithms. In finance, for identifying any arbitrage opportunities, especially Bellman-Ford for negative cycles. Game development, pathfinding in game maps, like Dijktras for AI character movement. Urban planning, modeling and optimizing transportation networks. In all these cases, if you see, we're trying to solve very large problems, and finding the shortest path is essential in order to identify what works and what doesn't. So consider mastering shortest path algorithms and combining the three techniques as well as and when required based on your application area. As we come towards the end of the lesson, a few key takeaways. Dijkstra's algorithm is efficient for graphs with non-negative weights. Bellman-Ford algorithm is versatile but slower. It is ideal for graphs with negative weights. Floyd-Warshall algorithm is suitable for dense graphs and all pairs shortest path problem. Choosing the right algorithm depends on the graph type, size, and edge weights. That's all for this lesson. Take the quiz next, test out your knowledge, and I'll see you in the next lesson.